In 1978, a soil lab in Manhattan, Kansas, the Kansas State University Soil Testing Laboratory, the most respected agricultural soil analysis facility in the state, received a set of soil samples from a farm in Lyon County. The samples were standard, 12 cores from a 160-acre field, mixed, dried, and submitted in a paper bag with the farmer's name and field number written in pencil. The lab ran the standard analysis: pH, organic matter, available phosphorus, available potassium, nitrate nitrogen, and the micronutrient panel. The results came back on a form that the farmer, a man named Alden Crouch, would keep in his desk drawer for 30 years because the form said something that nobody expected and that Alden refused to accept. The form said the soil was dead. Not in those words. Soil labs don't use the word dead. The form said organic matter 0.9%. Available phosphorus 4 parts per million. Available potassium 68 parts per million. Nitrate nitrogen below detection. pH 5.2. Cation exchange capacity 4.8 milliequivalents per 100 grams. For a non-farmer, those numbers mean nothing. For a farmer, or for a soil scientist, those numbers mean the soil has been stripped. Organic matter at 0.9% is functionally exhausted. Healthy tall grass prairie soil in Lyon County should run 4 to 6%. Available phosphorus at 4 parts per million is critically low. Crops need 15 to 25. Available potassium at 68 parts per million is below the response threshold. Crops need 120 to 180. No detectable nitrate nitrogen means the microbial community that converts organic nitrogen to plant-available forms has collapsed. The pH of 5.2, strongly acidic, means the soil has been depleted of calcium and magnesium bases that buffer acidity. And the CEC of 4.8 means the soil has almost no capacity to hold nutrients. They wash through like water through sand. The extension agent who reviewed the results with Alden, a man named Gerald Popp, 30 years with the Lyon County Extension Office, delivered the assessment with the practiced diplomacy of a man who's telling a farmer his ground is worthless. Mr. Crouch, these numbers are among the lowest I've seen in Lyon County. Your organic matter is at a level I'd associate with subsoil, not topsoil. Your nutrient levels are critically deficient across the board. The pH is acidic enough to lock up whatever nutrients are present. This field has been mined. Somebody took everything out and put nothing back. My recommendation is a heavy application of lime, phosphorus, potash, and nitrogen, approximately $85 per acre, to bring the field to minimum productivity. And even with that application, you'll need to rebuild organic matter over 5 to 10 years before the soil functions normally. $85 per acre on 160 acres, $13,600. That's the minimum to start. You'll need annual maintenance applications after that, approximately $40 per acre per year to sustain production. And the organic matter deficit will take a decade of cover cropping and residue management to address. Alden looked at the lab report. He looked at the field. 160 acres of thin, pale, crusted soil that he'd just purchased from an estate sale for $180 per acre, a price that reflected the soil's condition. The field had been continuously cropped to grain sorghum for 22 years by the previous owner, who'd applied no fertilizer, no lime, no manure, and no cover crop for the entire period. 22 years of harvest without return. 22 years of taking from the soil and giving nothing back. The field was, by the lab's measurement, exhausted. $13,600 to fix what 22 years of neglect broke. That's the chemical approach, the only approach, realistically. You can't grow a crop on this soil without inputs. The nutrients aren't there. The nutrients aren't there because the biology isn't there. The biology isn't there because the organic matter isn't there. The organic matter isn't there because nobody fed the soil for 22 years. You're proposing to fix a biological problem with a chemical solution. I'm going to fix a biological problem with biology. Stay with me, because what Alden did over the next 30 years, without spending $13,600, without buying a pound of synthetic fertilizer, and without following a single recommendation from the Extension Service, is why Kansas State University sent a research team to his farm in 2008 and called his soil the healthiest in the state. Let me tell you about Alden Crouch, because the man who bought 160 acres of dead soil wasn't a beginning farmer experimenting with an idea. He was a 60-year-old cattleman with 400 acres of well-managed pasture who understood something about soil that the lab couldn't measure, and the extension agent wasn't trained to see. Alden had been farming in Lyon County since 1955, 43 years by the time the lab report arrived. His primary operation was a cow-calf herd on native tall grass pasture. 80 head on 400 acres of Flint Hills grass that had never been plowed, never been fertilized, and never been planted. The grass grew because the biology worked. The buffalo had grazed these hills for 10,000 years before Alden's grandfather, Willard, had homesteaded the ground in 1891. The buffalo didn't fertilize. The buffalo didn't lime. The buffalo grazed, deposited manure, moved on, and let the grass recover. The cycle, graze, rest, decompose, grow, had built the soil that the Flint Hills were famous for. Deep, dark, rich, with organic matter levels of 5 to 7% and microbial communities so dense that a teaspoon of native prairie soil contained more living organisms than there were people on Earth. Alden understood this cycle because he'd been managing his pastures with it for 43 years. Rotational grazing, rest periods, manure recycled naturally. No synthetic inputs. The cattle were the fertilizer, the grass was the crop. The biology, the invisible army of bacteria, fungi, protozoa, nematodes, and earthworms in the soil, did the work of converting dead organic matter into plant-available nutrients. The system ran itself. It had been running itself for 10,000 years. When Alden bought the 160-acre field with the dead soil, he didn't see a chemistry problem. He saw a biology problem. The previous owner had killed the soil's biological community by starving it. 22 years of continuous grain harvest with no organic matter returned to the soil. The bacteria were gone because they had nothing to eat. The fungi were gone because their host plants, the diverse prairie species that support mycorrhizal networks, had been replaced by a monoculture. The earthworms were gone because the soil was acid, compacted, and devoid of the organic residue they needed for food and habitat. The lab measured the chemistry, the nutrients, the pH, the CEC. The chemistry was catastrophic. But chemistry is the result, not the cause. The cause was biological collapse. Fix the biology, and the chemistry fixes itself. Because the biological community is the nutrient cycling system. Bacteria decompose organic matter and release nitrogen. Fungi extend root systems and deliver phosphorus. Earthworms aerate the soil and mix organic matter into the profile. The entire nutrient cycle runs on biology. Kill the biology, and the cycle stops. Feed the biology, and the cycle restarts. If you're enjoying this story, consider subscribing to The Average Farmer. We share stories like this every week. Alden's plan was simple, slow, and free. He wasn't going to spend $13,600 on lime and fertilizer. He was going to spend zero on inputs and 30 years on patience. He was going to rebuild the soil the way the prairie built it originally, with biology, organic matter, and time. Step 1. Stop taking. The field had been continuously cropped for 22 years. Alden stopped. No more grain sorghum, no more harvest, no more removal of organic matter from the field. The first year, 1978, the field grew nothing intentionally. Alden let whatever was in the seed bank come up. Volunteer sorghum, foxtail, pigweed, lamb's quarters, ragweed. The weeds grew. They weren't pretty. They weren't productive. But they were alive, and alive was what the soil needed. The weeds grew, produced biomass, died in the fall, and lay on the soil surface through winter. The biomass, approximately 2,000 pounds per acre of dry matter in the first year, sat on the ground and decomposed. The decomposition was slow. The soil's microbial community was so depleted that the decomposition organisms were barely present, but some were there. Every soil, no matter how depleted, retains a residual microbial population, a seed bank of dormant organisms waiting for food. The weed residue was food. The microbes woke up. They ate. They multiplied. They started the cycle. Step 2. Add cattle. In the spring of 1979, Alden turned 15 head of cattle onto the 160-acre field. Not to graze the weeds. The weeds were mostly unpalatable. To deposit manure. 15 cows produce approximately 600 pounds of manure per day. Over a 90-day grazing period, April through June. That's 54,000 pounds of manure distributed across 160 acres, 337 pounds per acre. Rich, wet, biologically active manure containing billions of bacteria per gram, plus undigested plant fibers that provided food for the soil organisms, plus the nitrogen, phosphorus, and potassium that the manure contained as natural fertilizer. The manure was the inoculant. The weeds were the food. Together they rebooted the biological community. The bacteria from the manure colonized the dead soil. The fungi followed, arriving as spores in the manure and as wind-borne spores from the adjacent native pasture. The earthworms came last, migrating from the pasture into the field through the fence line, drawn by the improving organic matter levels and the reduced acidity as the decomposing manure buffered the soil pH. Everything was about to take 30 years, but Alden had one thing the lab couldn't prescribe: the patience to let biology work at biology's pace instead of chemistry's pace. Step 3. Plant diversity. In 1980, year 3, Alden overseeded the field with a native grass and forb mix: big blue stem, Indian grass, switchgrass, side oats grama, the 4 dominant grasses of the Flint Hills tall grass prairie, plus 15 species of native forbs, wildflowers, and legumes that added diversity to the plant community and, critically, added nitrogen through biological fixation. The legumes: Illinois bundleflower, purple prairie clover, lead plant, formed partnerships with nitrogen-fixing bacteria in their root nodules, pulling atmospheric nitrogen into the soil at no cost. The native species established slowly. The first year, the stand was thin. The dead soil couldn't support vigorous growth. But the plants that did establish sent roots deep. Tall grass prairie species root to 6, 8, 10 feet deep, reaching moisture and minerals that annual crops can't access. The deep roots pumped nutrients from the subsoil to the surface, a biological elevator that moved calcium, magnesium, and potassium from the mineral-rich subsoil to the depleted topsoil. Every fall, the above-ground growth died and added organic matter to the surface. Every spring, the roots extended deeper and brought more minerals up. The cycle accelerated. Step 4. Manage the grazing. Alden rotated his cattle through the 160-acre field, the same way he managed his native pasture. Intensive grazing for short periods, followed by long rest. He divided the field into 8 20-acre paddocks with electric fence and moved the cattle every 3 to 5 days. The cattle grazed the grass short, trampled the standing dead material into contact with the soil surface, where the decomposers could reach it, deposited manure uniformly across the paddock, and moved on. The paddock rested for 35 to 40 days before the cattle returned. The system was identical to what the buffalo had done on the Flint Hills for 10,000 years. Graze hard, rest long. The grazing triggered compensatory growth in the grass. The same response that Owen Metcalf's sheep triggered in his Kentucky pasture. The rest period allowed the growth to recover. The manure fed the soil, the roots went deeper, the biology expanded, the cycle turned. Let me tell you about the timeline, because the soil didn't recover in 1 year or 5 or even 10. It recovered slowly, measurably, and relentlessly over 3 decades. And the numbers tell the story of a biological resurrection that the chemical approach could never have achieved. 1978, organic matter, 0.9%, no crop, weed cover only, microbial activity, unmeasurable. 1983, year 5, organic matter, 1.4%, the weed residue, cattle manure, and first-generation native grass roots had added 0.5% of organic matter in 5 years. Phosphorus still low at 6 parts per million. But the pH had risen from 5.2 to 5.8. The manure and the decomposing plant material were buffering the acidity. Earthworm count, 3 per square foot, up from 0. 1988. Year 10. Organic matter, 2.1%. The native grasses were now dominant, big blue stem and Indian grass filling the field, the forbs blooming in summer, the root systems extending to 4 feet and deeper. Available phosphorus had risen to 11 parts per million, still below optimum but climbing, drawn from the subsoil by the deep roots and cycled to the surface by the decomposing leaf litter. Potassium at 98 parts per million, earthworm count, 8 per square foot. The soil was visibly darker. The pale, crusted surface of 1978 was being replaced by a darker, crumblier structure as the organic matter accumulated. That moment, the visible darkening, changed everything about how the neighbors viewed the field. And the farmers who drove past the Crouch property could see the difference from the road. 1993, year 15, organic matter, 3.2%. The field was halfway to the native prairie benchmark of 5 to 7%. The soil had crossed a critical threshold. At approximately 3% organic matter, soil structure changes fundamentally. The organic matter binds the mineral particles into aggregates, clusters of sand, silt, and clay, held together by microbial glues, polysaccharides, glomalin from mycorrhizal fungi, that create pore spaces for water and air. The soil becomes spongy. Water infiltrates instead of running off. Roots penetrate instead of being blocked. The soil breathes. Alden dug a shovelful and held it up. The soil was dark, almost black, crumbly, fragrant with the earthy smell of actinomycetes, bacteria that produce geosmin, the compound that gives healthy soil its characteristic scent. Earthworm count, 14 per square foot. The soil was alive in a way that the 1978 lab report said was impossible without $13,600 in chemical inputs. If you're enjoying this story, consider subscribing to The Average Farmer. We share stories like this every week. 1998, year 20, organic matter 4.1%, available phosphorus 18 parts per million. Within the optimal range for the first time, potassium 134 parts per million, adequate. Nitrate nitrogen 12 parts per million, supplied entirely by the biological fixation from legumes and the microbial decomposition of organic matter. pH 6.4, near neutral, buffered by 2 decades of calcium and magnesium cycling from the subsoil. CEC 12.4 milliequivalents per 100 grams, nearly triple the 1978 level, because organic matter is cation exchange capacity. Every percent of organic matter adds approximately 2 milliequivalents of CEC. The soil that couldn't hold nutrients in 1978 was now holding them because the organic matter was holding them. 2003, year 25, organic matter 4.8%. The field was approaching native prairie levels. The organic matter content was within the range of the never-plowed Flint Hills pasture adjacent to the field. The soil was, by every measurable parameter, a functioning tall grass prairie ecosystem. The grass was thick. The forbs were diverse. 23 species counted in a Transect survey, compared to 0 in 1978. The earthworm count was 22 per square foot. The water infiltration rate, measured by Alden with a simple ring infiltrometer, was 4.1 inches per hour, compared to 0.6 inches per hour in 1978. The soil was absorbing water 7 times faster than it had 25 years earlier. Alden was 85 years old. He'd been watching this field for 25 years, measuring it every November, recording the numbers in a ledger, tracking the organic matter, the pH, the nutrients, the earthworm count, the species diversity. 25 years of annual data, 25 data points on a curve that started at 0.9% organic matter and was now at 4.8%. A recovery rate of approximately 0.16% per year. Slow by industrial standards, inexorable by biological standards. And then Kansas State came. Let me tell you about the university visit, because the research team that drove to Lyon County in 2008 found something they weren't looking for. And the data they collected contradicted 30 years of Extension Service recommendations about how to rehabilitate depleted soil. Dr. Karen Nichols was a soil ecologist at Kansas State University. Her research focused on soil biological communities, the bacteria, fungi, and invertebrates that drive nutrient cycling in agricultural soils. In 2007, she'd begun a study of soil health across Kansas. sampling farms with different management histories to quantify the relationship between management practices and soil biological activity. A colleague in the Lyon County Extension Office, Gerald Pop's successor, mentioned the Crouch Field. There's a farmer outside of Emporia who bought a dead field in 1978 and has been rehabilitating it with cattle and native grass for 30 years. No fertilizer, no lime, no chemicals. The field is a functioning tall grass prairie now. The organic matter went from 0.9 to something above 4%. You should look at it. Dr. Nichols drove to the Crouch Farm in April of 2008. Alden was 90. His son, Mitchell, was managing the cattle operation, but Alden still walked the 160-acre field every week, slowly, with a cane, but walking. He met Dr. Nichols at the gate. "Mr. Crouch, I'm studying soil health across Kansas. Your extension agent told me about your field, the rehabilitation from depleted soil to native prairie over 30 years. 30 years, and zero fertilizer. The cattle did the work. The grass did the work. The biology did the work. I just managed the timing." Doctor. Nichols spent 3 days on the Crouch Farm. She collected soil samples from the rehabilitated field and from the adjacent, never-plowed native pasture, the control, the benchmark, the soil that represented what Lyon County ground looked like before European settlement. She ran the standard soil chemistry analysis. She also ran something the 1978 lab hadn't, a biological analysis. Microbial biomass carbon, the total weight of living microorganisms in the soil, soil respiration rate, the rate at which organisms consume organic matter and release CO2, a direct measure of biological activity. Mycorrhizal colonization, the percentage of root length colonized by beneficial fungi. Glomalin content, a glycoprotein produced by mycorrhizal fungi that acts as a soil glue, binding aggregates. And water-stable aggregates, the percentage of soil that holds together when submerged in water, a measure of structural integrity. The chemistry results were impressive. Organic matter, 5.2%, higher than the 2003 reading, still climbing. pH, 6.6, available. P, 22 parts per million, available K, 156 parts per million, CEC 14.8. Every chemical parameter was at or above the optimal range for tall grass prairie production. The soil that the 1978 lab had declared dead was now, by the same lab standards, among the most fertile in the county. But the biological results were extraordinary. Microbial biomass carbon, 680 micrograms per gram. The state average for cropland, 180. The Crouch Field had nearly 4 times the microbial life of an average Kansas farm. The adjacent native prairie, the never-plowed control, measured 720. The rehabilitated field was at 94% of the native prairie's biological activity. After 30 years of management, the biology had recovered to within 6% of the undisturbed native soil. Mycorrhizal colonization, 82%. State cropland average, 15 to 25%. Native prairie, 88%. The fungal networks, the underground internet that connects plants, delivers nutrients, and communicates stress signals, had re-established on the Crouch Field to a density that matched the native prairie within 6%. Glomalin content, 4.2 milligrams per gram. State cropland average, 0.8. Native prairie, 4.6. The fungal glue that holds soil aggregates together, that prevents erosion, holds water, and creates the structure that makes soil alive instead of dead, was at 91% of the native benchmark. Water-stable aggregates, 74%. State cropland average, 22%. Native prairie, 81%. 3/4 of the soil in the Crouch Field held together when submerged, compared to less than a quarter on the average Kansas farm. The soil wasn't just chemically recovered, it was structurally recovered. It held together, it held water, it held nutrients, it held life. Dr. Nichols sat in Alden's kitchen and told him what his soil had become. "Mr. Crouch, your field has the highest soil biological activity of any rehabilitated site I've measured in Kansas. The microbial biomass, the mycorrhizal colonization, the glomalin content, and the aggregate stability are all within 6 to 10% of the adjacent native prairie, soil that has never been plowed. Your field was at 0.9% organic matter in 1978. It's at 5.2% now. The biology is functioning at native prairie levels. This is the healthiest soil I've measured in the state. The healthiest soil in the state was the deadest soil in the county 30 years ago. The deadest soil became the healthiest because you fed the biology instead of the chemistry." The extension recommendation in 1978 was $13,600 in chemical inputs, lime, fertilizer, nutrients applied from a bag. That approach would have raised the nutrient levels immediately but wouldn't have rebuilt the biology. The biology is the nutrient cycling system. Without biology, the chemical inputs leach, erode, and volatilize. You have to keep applying them every year because the soil can't hold them. With biology, the soil holds nutrients because the organisms are the holding capacity. They absorb nutrients, store them in their biomass, and release them when they die and decompose. Your soil doesn't need fertilizer because your biology is the fertilizer. My father told me that in 1958. He said the soil is alive, and if you feed it, it feeds you. The extension says the soil is a medium, and if you add chemicals to it, crops grow in it. Those are two different philosophies. My father's philosophy built the soil. The extension's philosophy mined it. That moment changed everything about how Dr. Nichols framed her research. And the data from the Crouch Field would never let the soil science community forget that biology builds what chemistry can only borrow. Let me tell you about the JD dealer, because the equipment angle in this story is about what Alden didn't buy, and the dealer who spent 30 years trying to sell it to him. Ray Holcomb ran the John Deere dealership in Emporia. He sold tractors, planters, sprayers, and fertilizer application equipment, the machinery of chemical agriculture. For 30 years, he'd watched Alden Crouch manage the 160-acre field without buying a single piece of application equipment, without purchasing a single bag of fertilizer, and without using a single gallon of herbicide or pesticide. Ray had tried. In 1979, he'd quoted Alden a lime spreader and a fertilizer buggy, $6,200 combined, to apply the inputs the Extension Service recommended. Alden declined. In 1985, he'd offered a no-till drill for $14,000 to seed cover crops into the field. Alden declined. He overseeded by broadcasting from the back of his Farmall 560, scattering seed by hand the way his grandfather had seeded pasture in the 1890s. In 1995, he'd offered a chemical sprayer for $8,500 to control the weeds in the native grass stand. Alden declined. The weeds were the forbs, the legumes, the nitrogen-fixing wildflowers that were doing the work the sprayer would have destroyed. In 30 years, Alden's total equipment expenditure on the 160-acre rehabilitation, zero. He used the Farmall 560 for fence work and for moving cattle between paddocks. He used electric fence and steel posts for the rotational grazing system. He used a hand-crank seeder for the native grass and forb overseeding. Total input cost over 30 years, approximately $2,400. Seed for the native plantings, $800 over 3 seeding events. Electric fence supplies, $1,200. And soil testing, $400 for 30 annual tests at approximately $13 each. $2,400 over 30 years. The extension recommendation of $13,600 in year 1 alone was more than 5 times what Alden spent in 3 decades. And the annual maintenance of $40 per acre that the extension recommended, $6,400 per year, $192,000 over 30 years, was never spent. Alden's total savings over the chemical approach, approximately $205,000, and his soil was healthier. Not just healthier than the 1978 dead field, healthier than any actively farmed soil in Kansas. The chemical approach would have maintained nutrient levels, while the biology continued to decline. Alden's approach rebuilt the biology, while the nutrient levels recovered on their own. One approach treats symptoms, the other cures the disease. Ray drove to the Crouch farm after the K-State study was published. A summary appeared in the Kansas Farmer magazine in 2009 with Alden's photograph and the headline, "Dead to Alive." 30 years of biological soil rehabilitation. Alden, Ray, Kansas State says your soil is the healthiest in the state. Kansas State measured what I've been watching for 30 years. The soil got darker every year. The earthworms came back. The grass got thicker. The water soaked in instead of running off. I didn't need a university to tell me the soil was alive. I could see it. I could smell it. I could feel it in my boots. The university just put numbers on what my boots already knew. I've been trying to sell you equipment for 30 years. Lime spreaders, fertilizer buggies, sprayers, drills. You didn't buy any of it. I didn't need any of it. The cattle spread the lime. Their manure buffers pH. The cattle spread the fertilizer tune. Their manure contains NPK. The native plants are the cover crop. They grow without being drilled. The diversity is the weed control. A diverse plant community doesn't have weed problems because the weeds are part of the community. Everything the equipment does, the biology does for free. The equipment costs money. The biology costs patience. I had patience. I didn't have money. You saved $205,000 by not buying inputs. I saved $205,000 by trusting the biology to do what biology has been doing for 10,000 years. The Flint Hills weren't fertilized by John Deere. They were fertilized by buffalo. My cattle are the buffalo. The grass is the prairie. The 30 years was the time it took for the cycle to restart after 22 years of abuse. That's the exchange rate. 22 years of mining requires 30 years of healing. The soil keeps a ledger. You can't cheat the ledger. Let me tell you about the aftermath, because the K-State study attracted attention that went beyond Lyon County and beyond Kansas. Dr. Nichols published the Crouch Field data in the Soil Science Society of America Journal in 2010. The paper documented the 30-year rehabilitation trajectory, annual soil test data from 1978 to 2008, biological assay data from 2008, comparison to the adjacent native prairie, and the management history that produced the recovery. The paper's conclusion: biological soil rehabilitation through managed grazing and native plant restoration can achieve soil health parameters equivalent to undisturbed native prairie within 25 to 30 years without synthetic chemical inputs at a cost that is approximately 1% of the chemical rehabilitation alternative. 1%. $2,400 versus approximately $205,000. Same result. Functional, productive, healthy soil. Different method, biology versus chemistry. Different timeline, 30 years versus immediate, but requiring annual maintenance indefinitely. Different philosophy, feed the soil versus feed the crop. The paper was cited 143 times in the first 5 years, a high number for a soil science paper, indicating that the research community found the data significant. The Crouch Field became a case study in soil health courses at 3 universities. The USDA Natural Resources Conservation Service cited the paper in its updated Soil Health Technical Note in 2012, which recommended managed grazing and diverse plantings as a soil rehabilitation strategy for depleted cropland. 7 farmers in Lyon County visited the Crouch Field between 2009 and 2012. 3 of them began biological rehabilitation programs on depleted fields on their own properties, converting exhausted cropland to managed grazing with native grass plantings, following Alden's 30-year model. The results, after 5 to 8 years, showed the same trajectory. Organic matter increasing, pH stabilizing, earthworm populations growing, water infiltration improving. The biology was restarting. The soil was healing. The ledger was being balanced. Let me tell you how this ends. Alden Crouch died in 2012 at 94. He'd been walking the 160-acre field every week until 2010. 92 years old, cane in hand, boots in the soil that he'd brought back from the dead. Mitchell, Alden's son, continues to manage the field with the same rotational grazing system. The cattle graze, the grass grows, the biology cycles, the organic matter continues to increase. The most recent test in 2023 showed 5.8%. Still climbing, still building. The soil is not done healing. Biology doesn't stop when the farmer does. The Farmall 560 is in the barn. Mitchell uses it for fence work and paddock moves. The same jobs Alden used it for. The electric fence charger that powers the 8-paddock rotation is solar powered. A panel Alden installed in 2001. One of the few purchases he made for the field. The charger, like the biology, runs on the sun. The lab report from 1978 is in Mitchell's desk. The same drawer where Alden kept it for 30 years. Organic matter, 0.9%. The numbers are faded, but legible. Mitchell keeps it beside the most recent lab report. Organic matter, 5.8%. The 2 reports, 30 years apart, tell the story of what patience and biology can do to soil that the experts said was dead. Gerald Popp, the extension agent, who recommended $13,600 in chemical inputs, retired in 2001. He visited the Crouch Field in 2005 at Alden's invitation. He walked the field, dug a shovel of soil, counted earthworms, and stood in the tall grass prairie that had grown from the dead ground he'd assessed 27 years earlier. I told you this soil was dead in 1978. I prescribed chemicals. You prescribed patience. My prescription would have worked faster. Your prescription worked deeper. The chemicals would have raised the nutrient levels, but not the biology. The biology raised everything: nutrients, structure, water-holding capacity, resilience. You built something the chemicals couldn't build. You built a living system. My father built the philosophy. I built the patience. The soil built itself. I just stopped preventing it. If this story stayed with you, subscribe to The Average Farmer for more. We'll see you in the next one. The lab measured chemistry. The farmer fed biology. The soil wasn't dead, it was starving. And the man who fed it what the lab couldn't measure, time, manure, diversity, rest, brought it back from the grave. 0.9% to 5.8%. 30 years. Zero fertilizer. $2,400 total cost. The healthiest soil in the state. Grown from the deadest field in the county. By a farmer who trusted the biology that built the prairie and refused to replace it with chemicals that couldn't. Because the soil keeps a ledger. 22 years of taking requires 30 years of giving. The exchange rate is not negotiable. The biology is not optional. And the man who feeds the soil instead of the crop ends up with both.